Recording?
What we are going to start with is before we just start discussing the control system process, what we'll do is we'll take a look at Laplace transforms. Have you heard about Laplace transform?
Yes.
Have you done one of any of your math courses?
Yes.
We're going to do Laplace transform. Really? Yeah. So please make sure it is recording because in yesterday's class it stopped midway. Just keep an eye. So why do we use, let's look at first why we use Laplace transform. Okay. You've used differential equations, right? You've learned differential equations.
Yeah.
Why do we use differential equations?
It's a model system.
To model systems, exactly. What makes engineering systems precise? Or what makes it, let's say, reliable, scientific? What is the difference between an engineered system and, let's say, an art? For example, any engineering system, what is the basis for any engineering system? The basis.
Physics.
Physics and mathematics. Okay. What makes an engineering system precise is mathematics. What you can do is you can actually model it and you can prove that it's reliable. And this is in tune with nature. Nature itself is mathematical. Okay. So Laplace transform, as everyone said, differential equations are used to model systems. Okay. What do you do with the model once you do a model? So what is a model? What is a model? Model it's essentially a problem statement. It's a mathematical problem statement. Okay. So once you model it as a differential equation, that's your problem statement. Now you need to figure out a solution for that problem. So you have heard about when you do your differential equations, a lot of the focus is on the solution of that particular differential equation. Laplace transform, what it does is it takes a differential equation let's say this is how it's denoted. It takes a differential equation. What is a differential equation? Is in time domain, right? F of S. Okay. This is how Laplace transform is defined. This is capitalized L. So this is how you read it. The Laplace transform of any function of time. Now here this would generally be a modeled differential equation. Whatever is in this bracket, in the square bracket. The Laplace of any function of time denoted by capital F of S. S is the Laplace variable, or it's a frequency variable, is defined as integration of that function f of t e to the power of minus st dt.
So, times 5.
Okay? So that is how your Laplace transform is defined. What we are going to do is, we are not going to use this definition a lot. We're going to use mostly tables. So what you're trying to do here is, you understand the relationship between time and frequency?
Yeah.
What is the relationship between time and frequency? Anyone?
Isn't it
Frequency is how many times?
per unit time?
Frequency is per unit time, right? So they are interconvertible. So you should be able to see systems either as a function of frequency or function of time. Okay? So as time progresses, how the system changes. That is what is modeled here. You can also do that as frequency changes, how the system changes. So that is what Laplace does. That is the Laplace transform. Okay? And the inverse of the Laplace transform, this is Laplace transform. And what would be the inverse Laplace transform? Denoted by L inverse of f of s. So you're converting from frequency to back to time. Okay?
Dr. Sunday,
Yes.
for the Laplace transform definition you wrote up there, you said 0 negative to what?
Infinity.
Oh, okay.
0 to infinity. Okay? This is how your inverse Laplace transform is defined. So what we're trying to do is, this is how we're going to use Laplace transform. When you're modeling systems, where do you start?
Where you start?
Where do you start? if I ask you to model, let's say, an aircraft, not an aircraft. Let's look at something more simple. Huh? Yeah, you can take that, or let's say you want to model this table. Okay? What is your basis? Where do you start? How do you start modeling systems?
What's an equation that represents
How do you develop that equation?
based upon, wouldn't be based upon what you're trying to model, like not what you're trying to model, but the specifics of that system or that model, whatever you're trying to model. Like for the table, I would probably use the area equation as a basis for my equation.
Okay.
Because it represents.
Let's say you're trying to model the lift or drag produced by an aircraft. The lift produced by an aircraft. Where do you start?
I would start with 1.5 row V infinity squared. So I'll start. Or something that models the lift. Like the equation for the lift. You know what you
Anyone? No? Where do you start? See, your aerospace fundamental, or aerospace, is developed on something. What is at the foundation of all of aerospace engineering?
well, I would say math, but I don't feel understand the question. Why? You want?
At the foundation of aerospace engineering is physics. Okay? You start with physics. Physics is your starting point for everything. Math cannot get you started. Math can let you navigate once you start, but math cannot get you started. So what are physics? Laws of physics. For example, Newton's laws are fundamental to everything you learn in aerospace engineering. In fact, for that matter, any engineering, Newton's laws are fundamental. Newton's laws, for example, if you're talking about Kirchhoff's laws, electrical engineering, you're talking about Kirchhoff's laws. Again, Kirchhoff's laws are based on Newton's laws, but they are more directly applicable to electrical circuits. But for aerospace engineers, you have to know where it all starts. It all starts at Newton's laws. That is where it starts. There is nothing we know as aerospace engineers before Newton's laws. As a precursor to Newton's laws, there is nothing we know. As physicists maybe, but not as aerospace engineers. Our foundation is Newton's laws. So we start at Newton's laws. When you start Newton's laws, you end up with this f of t. Right? You use more often than not, you're going to use Newton's second law. Okay? Which is force is equal to mass into acceleration, or the applied force is equal to change in linear momentum. That is what we are going to use more often than not. And of course, we are going to use Kirchhoff's laws. When you apply that to any system, right, you'll end up with this. Now, what this Laplace transform will let you do is, it will first let you convert the time domain model into a frequency domain. There are a set of solutions, a more direct set of solutions for frequency domain. So you'll solve the problem in frequency domain. Use the inverse Laplace to convert that solution to again time domain. Right? You see it? You take a time domain problem, you convert that problem into a frequency domain using Laplace transform. Frequency domain has much direct solutions. So what you do is, you take the solution, you solve the problem in frequency domain, you take the solution and you convert that back to time domain. So you have a time domain problem and a time domain solution. You understand? So that is how you are going to be able to use.
So we work with the problem and frequency.
Huh?
We work with the problem and frequency.
Yes, you will work with problem in frequency domain.
And then convert it.
Convert it back to time domain. We understand, most of us understand time domain much better than frequency. So, but there are very direct solutions, linear solutions in frequency domain. Very systematic solutions. And that is what we are trying to do. We are trying to use those tools available in this frequency domain to get very direct solutions and then convert that back to time domain so that we can understand them better. You can do a time domain plot, right? If you have time on the x-axis, the problem statement on the y-axis, if you do that, you'll know how the problem evolves as time progresses. Now from the textbook, we're going to use table 2.1 and 2.2. Table 2.1 is Laplace transform and table is equal to A over S plus. Okay.
Question. Is that why they got the, that's where they get it in the formula sheet, right? That's where they get that in the formula sheet. No, the formula sheet it says e to the at with positive.
Right. So your formula sheet will give you this.
Correct.
Okay. So you may get a problem where the solution is already in your formula sheet. In that case, you cannot just write the solution. You have to show the process, of course. But you have, you already have a solution in hand. So this is about Laplace transform. We are going to take a look at Laplace transform a little bit more in detail. But what we need to address is we need to take a look at partial fraction expansion. You heard about partial fraction expansion? You remember? You heard about partial fraction expansion? No?
Yeah.
You remember partial fraction expansion?
Yeah.
Okay. Why do we need partial fraction expansion? We need partial fraction expansion because Laplace transform, your tables as you see, are defined for relatively simple functions. Okay? If it's a complex function, you remember what an improper fraction is? What is an improper fraction?
When the numerator is greater than the denominator.
705. That's an improper fraction.
What is it? What is an improper fraction? As Matthew said, the numerator is greater than the denominator. Now, Laplace transforms, in a sense, are defined for proper fractions. So if you have an improper fraction, you may have to convert that to proper. This is just one example, but let's take a look at it. So you have something like this. So if you have something like this, okay, thing you need to realize is you will not find a direct Laplace transform or Laplace inverse of such a transform. What is the time variable? What is the time variable in this?
What is time?
Yeah, which one is the time variable in this? T. What is S?
Frequency.
It's a frequency variable. It's the equivalent. It's called the Laplace variable or the frequency variable. You have to keep that in mind. Okay. Just like your f of t could be a differential equation. When you do Laplace transform, you end up with polynomials in Laplace variable. Does that make sense?
Yep.
Polynomials in Laplace variable. So you see there is a polynomial in the numerator and polynomial in the denominator. What is the order of the polynomial?
Third.
Third, right? So you have a third order polynomial and the second order polynomial. This is an improper fraction, in a sense. Okay. So the first thing you do is you make it into a proper fraction. So if you are given two polynomials, do you remember dividing a polynomial by another?
Yes.
Yes, subtract.
Okay. So this is how you divide, and show this once, you have to keep this in mind. So you have s cubed plus 2s squared plus 6s. This goes under the hat, right? Under the heart, sorry. You have s squared plus s plus 5. Can you divide this? Where do you start? What is the first one? Huh? How do you start?
You align the order with the order.
You start straight to look at. You
The
try to
first.
eliminate
The first.
the left hand.
So it'd be like that raised to whatever would equal x.
Right. So you start with s.
X.
Okay. It is s cubed plus s squared plus 5s. Got it?
Yeah.
So you have minus, minus, minus. That is how you do division, right? If this goes, you have s squared plus
6 x. Oh,
s
x plus
plus
7.
7. Okay. Then you have plus.
Hold up, time.
What is it? 1. S squared plus s plus 5. Minus, minus, minus. And you have
2.
So now you can write this as f1 of s is equal to s plus 1 plus 2 over
S plus 1.
s squared plus s plus 5.
Is there a
I always forgot how to do
this?
You can do it again.
Man.
But
That was a
I
long
don't
time
understand
ago.
the-
That was a long time ago.
You class it up to line 30. Okay?
Huh?
Class it up to line 30. It's not line 30.
Yeah.
Okay?
Yo, I remember that. I remember that from like, I think that was high school.
Does this make sense, everyone? Now we're going to find, if you want to find the Laplace transform of this one, okay? So take a look at what we're doing here. These are three different, you can read this as three different terms. You have S, this thing, and this thing. Okay? There is a simple solution to this, there is a simple solution to this. Again, this one does not have a simple solution. If you look at the table, the table defines Laplace inverse for simple functions. The denominator is only a first order polynomial.
Yes.
So you have to convert this to a first order polynomial.
Right.
Okay. So how do you do that?
You have to factor before the.
That is where we use partial fraction expansion. Okay. So this is not partial fraction expansion. Whatever we have done, this is not partial fraction expansion. This is just division. Okay. You take this. Let's call this A.
Should we complete the square?
A is equal to 2 4 x squared plus 1. There will be 3 cases. There will be 3 cases of partial fraction expansion. Case 1 is roots of denominator are real and distinct. Case 2, roots of denominator are real and repeated. And case 3, roots of denominator are complex or imaginary. Okay. When you're doing the partial fraction expansion, you encounter one of these cases. It cannot be anything other than this. The roots of this denominator could either be real and distinct, or they could be real and repeated, or they could be complex / imaginary. Okay, what is the difference between complex and imaginary?
Complex has a real
Real part and imaginary part. Imaginary is pure. We're going to take examples, and I'm not going to tell you, I'm not going to discuss the theory behind this. We'll just take an example and then see how we get to the partial fraction expansion of that example. Let's start discussing case 1. Roots are real and okay. So this, take a look at this. Or we'll take another example. So if you have, let's say, f1 of s is equal to